Usually concentration depends on how many people this wastewater treatment plant is served. In terms of concentration, typical BOD concentration, 200 medium strength wastewater treatment plant, but it can go anywhere from 150 to 350 depending on the characteristic of So organic loading, it's the main consideration, one of the main pollutants. Together with the organic loading, so BOD, biochemical oxygen demand, we'll talk a little bit more. The solid present in the wastewater, TSS, we use the total suspended solids, is the amount of solids present in the water that create a turbid, that made water turbid. And again, this is going to affect, if untreated, the receiving water bodies. So the two main contaminants of interest, at least at the federal level, they are BOD and TSS. Biochemical oxygen demand, total suspended solid. Typical value, average value, 240 milligram per liter, but medical finance anywhere between 100 and 400. It all depends if it's a combined sewer. Does it have industrial contribution? So those are, of course, average value. It's more of a range that we observed. Now, wastewater is characterized also by other pollutants, and we're going to do some exercise on those as well. Nutrients such nitrogen and phosphorus are present in wastewater, and nitrogen in mainly form of organic and ammonia that's present. So organic nitrogen and ammonia nitrogen. It's usually 35 milligram per liter. This value are, again, only typical value. And phosphorus has organic phosphorus and mainly orthophosphate. So organic P plus PO4, that's orthophosphate, 10 milligram per liter, that's present. So those are your typical contaminant present. Now I'm missing one fundamental contaminant that are pathogens, right? Microorganisms that can get people sick. So at the federal level, every wastewater treatment plant has to treat BOD, TSS, and pathogen. So those are the three main contaminants that a wastewater treatment plant need to be able to reduce. And so on the federal level, every wastewater treatment plant has to request a permit to be able to discharge the wastewater into a receiving stream. The permit, NPDES permit, probably you've heard about it, NPDES, NPDES permit, stands for National Pollution Discharge Elimination System permit. Every plant, every utility that discharge into water of the United States, in this case river, lake, or whatever, they need to request a permit. Every 5 years, they have to request a new permit. They will tell you how much flow they can discharge. The BOD has to be less than 30 milligram per liter. The TSS has to be less than 30 milligram per liter. And then there is also on the equal count for pathogen. There are specific requirements in terms of the flow depends, the number depends on the flow, so it's not a fixed number. And then nitrogen and phosphorus, there is not a national regulation based on nitrogen and phosphorus limit, but these are stream, like it's a specific to receiving water body. What does it mean? If my wastewater discharge in a sensitive area that has little recirculation, that could be like an enclosed bay or a lake, then you might have more stringent limit if you are discharging an open water. Boston, for example, does not have any limit on nitrogen or phosphorus. It's very small treatment plant that discharge in Narragansett Bay or the Chesapeake Bay that have a very stringent limit on nitrogen and phosphorus. So these are always site-specific. These are the national, the federal regulated value. At least you have to have what we call secondary treatment. Secondary treatment standard are this. So every wastewater need to treat at least BOD and TSS below those value. If you discharge to a very sensitive area, you might be required to also reduce nitrogen. Could be less than 10, could be less than 3. Phosphorus could be less than 1, could be less than 10 microgram per liter. So it's very site-specific. And so that's why the permit, it's specific to that facility, but all of them will have to have at least this minimum requirement. How do we go from this BOD value, this organic loading and solid loading, and this nitrogen and phosphorus loading, if we're doing advanced, to this value? Well, at a wastewater treatment plant, we do various treatment, physical, chemical, biological treatment that reduce those loads. So here I highlight the water line, so how the water flow at the plant. So we have our influent with this characteristic, right? Has all of this contaminant in it. The first step is what we call preliminary treatment. Preliminary treatment is mainly physical treatment. We have flow measurement, just because we need to know what is the flow. Even your permit will give you what is the flow that you can treat. Pump, we need usually all the process. It's a gravity flow, so we increase the head at the beginning of the plant so that it can then flow through gravity for the whole during the whole plant. We have a screening, and screening is simply metal bar with that given opening so that every material larger than the screen opening is going to be retained. The order is not this necessarily. The screen usually comes before the pumps, so that the idea is to remove those large objects before you send it to a pump room. So this is to remove, screen, remove solids. But the solids here, these are suspended solids, these are the fine solids, not the large one that can be removed in a screen. So when we talk about suspended solids in the micron range, and we're talking here remove settable and large solid like rags and stuff that could be present in the sewer line, and that can, like sand, can also affect the lifetime of your pumps impeller. Other part of the preliminary treatment, it's what we wanted to remove solids, especially those solids that can settle fast. So we have a Greek chamber. And oftentimes it's an aerated Greek chamber. And so the shape, it could be different than, it's usually a rectangular channel where you insufflate air to avoid also that smell, like the septic smell, start aerating the system. But the air, it's actually to help us with the removal of settleable solids, and mainly grit and sand. So a grit chamber is to remove a larger particle that can settle quickly in order of minutes. We're not doing a problem on grid chamber, but it's very simple, the design. Usually it's for the residence time, it's 2-3 minutes. You have your flow. You can determine the size of the tank based on that residence time. And the airflow, usually it's part of the design as well. There is a range that you have to do, how many cubic meter per cubic meter or flow that you are treating. So very simple calculation in that case. So the screen remove solids, grid chamber remove. Sand and grids. Usually the solids collected in the screen and the solids collected in the grid at the bottom of the grid chamber are put into a hopper and sent directly disposed to a landfill. So there is no further treatment at the plant of these solids. It's pretty, there is some organic in that, but it's mainly heavy solids present. So at the plant, we don't care anymore about those flow, right? Now we have water that comes from the preliminary treatment that has been removed some of the solid, the heavy solids. The rest, after this, we're still removing solids. However, these are solids that are settled in a couple of minutes, or they are large enough to not pass through like a 1 inch or half an inch opening in a grid system. What we care here is remove suspended solids. Suspended solids is what we are trying to remove. A primary treatment or sedimentation basin, it's a physical treatment. Slow down the flow, slow your flow. The flow is slow enough that a particle can settle out of the solution and be collected at the bottom. Okay, I'm gonna erase this part so that we have a little bit more space. So it's a physical process. It's gravity. So you use gravity to settle out suspended solids. When suspended solids are small solids that make the water turbid, and they are in the order of microns. So less than 1 micron really we consider. How do we remove the suspended solids? So we make a large enough tank and make the flow slow down so that it can settle at the bottom. We'll do a couple of problem on the design of this specific area, but suspended solid removal. That's what a primary treatment does. We can also remove something else here. Floatable, like grease and oil, in the sedimentation basin will float to the top. So I'm going to have suspended solid here. I'm going to have grease and oil at the top. We have skimmer that can remove the oil and grease at the top. Usually a primary sedimentation achieve a 50% to 60% suspended solid removal. And since remove organic like oil and grease and some organic that settle at the bottom, we usually achieve 30 to 35% BOD removal. The removal here, it's mainly physical. It's just because some of the organic settle out and some of the grease float on top and the base came out. So these are typical removal that we achieve in the primary treatment. All right. Now, TSS, even if it's 60%, we are not nearly close to that. Where we need to get 30, and even BOD, not even close, right? So we need to get something else. In the past, EPA allowed, I think there is the only one plant that still does, it's in San Diego, advanced primary. So you add a coagulant, add a chemical treatment to the primary to increase the TSS and the BOD removal so that you can get close to those numbers. It's not allowed anymore. They don't allow just the advanced primary. You have to have a secondary biological process. I think San Diego was the last one permitted plant to operate like that, and I think since then it's been also upgraded. So we remove solids. We still need to remove some other important contaminants, the BOD, the organic content. This is done in what we call the secondary treatment. It's a combination of biological process and physical separation, where we have bugs that eat the organic, make up solids, and the solids settle out in a sedimentation. The process at steady state reduce 90% to 95% BOD, and at the sedimentation reduce 90% to 95% of the solids. So at the end, we are able to remove BOD and TSS. So this is bioprocess, bio. This is again physical. We're going to be doing a problem on this part, so we'll go back a little bit. How does it work? But essentially, you have air that it's added. Air, you have food, that is the BOD. You have the workers, that are the bugs, and the process, that's accelerated degradation of organic in a confined space. So the soluble compound becomes particulate, so solids, and then you physically separated the solids. So this achieve BOD 95 to 99% BOD removal, and 99% total CS removal. At the end of our secondary, we have pretty much should have achieved, if designed properly, our TSS and BOD goals. The only thing left to remove based on pathogen here. Usually it's based on E. coli, less than 0 count, total forming, most probable number, depending on the way that the permit is written. We need to remove the pathogen. How do we remove the pathogen? Usually, chemically is the most common way to remove pathogen, which is with the addition of chlorine or hypochlorite, so bleach essentially, to kill the pathogen. So chemical treatment of the water. Other option is UV or ozone. So those are all 3 disinfection methods to remove pathogen. At the end of this train, we have removed the 3 main contaminants. Water is safe to be discharged into the receiving water body. If nitrogen or phosphorus need to be done, we need to add additional process that are either chemical or physical or biological process. We'll have at least one problem on nitrogen. We won't do much on phosphorus. That's way advanced for the peat. It's really any problem on peat removal. Any question about this? Yes.
So basically get rid of pathogens at the last stage?
Mm-hmm. Yeah, pathogen are removed after all of this other process. Disinfection is always before discharge. Now, if it's adding bleach or or chlorine gas, we need to make sure that there is no residual. We will see when we do water supply, we wanted to leave a residual in the pipe. In the case of wastewater, we don't want any residual because that will kill the fish in the river, right? So usually if it's chlorination, we also have dechlorination. So chemical addition and other chemical to eliminate the excess chlorine that usually is had to make sure that the pathogen are killed. If it's UV or ozone done disinfection, then they don't have any residual, so you won't have to do any further treatment. But that's pretty much it. On the secondary standard, that's usually what the PE requires, just the secondary standard. All right?
How about nitrogen?
Nitrogen and phosphorus are mainly removed nitrogen is mainly removed biologically in the biological unit making modification, and we'll talk a little bit in one of the problem. Phosphorus can be removed biologically, again, changing the configuration and changing this bioreactor, or can be done chemically with addition of a coagulant, ferric, and alum, and usually the addition can be done before the primary treatment, or if it's very advanced, you will do after as a tertiary process with filter and chemical and additional. I did not see any problem that does any design of those components, but and it would be only in the afternoon, and will be one problem maybe of the whole thing. So we are not going to be talking about, if you're interested. Phosphorus and nitrogen removal actually are my area of expertise, so that's why I don't do it, because otherwise I'll talk for like 5 hours. All right, so this is the overall for the water line. Now there are residual and solids produced in this process that need to be further treated. We have talked about the solid, the residual on this side, and those get disposed in a landfill. What comes at the bottom of the clarifier, it's primary sludge. And what comes at the bottom of the secondary clarifier, it's secondary sludge. This needs to be further treated. I don't want to complicate this drawing. We do a problem on additional sludge treatment in one of the exercises, so we'll talk a little bit about that. All right? So let's try to do problems so that we can get a little bit our ends theory on this. And I guess, I could just put it there. Put it here. Let's try to use this so we don't. All right. So let's try to do the everybody got a handout? Yeah. All right. So there are additional problems in the one that I posted, that I sent you, but I select a few so that we have a little bit of everything. So the first problem is we have a community with a population of 25,000 is planning to expand its wastewater treatment plant. Using the table below for daily flow and assuming a 15% population increase over 5 years, and the peak factor being 2.5, what is most likely the peak flow at the end of the 5 years time? All right, so how do we estimate flow? In this case, the information that are provided to us are, the table gives us the daily water use or wastewater production, both commercial and domestic. And we have the population, it's currently 25,000, but it's expected to increase by 15% in the next 5 years. We wanted to determine the flow rate. Now the flow rate average flow rate is going to be the water demand, so the per capita, the gallon per person per day, so that water usage per day by person, multiplied the number of people, right? This will be the average. The peak factor that is provided to us, it's the Q peak over Q average, which means that the Q peak in 5 years, right? At the end of the 5 years, it's going to be my Q average by my peak factor. All right? Now we need to determine what is the population at the 5 years and what is the water demand at the 5 years based on the information provided. So in our case, the population now is 25,000. We have an increase of 15%. So my total population will be 25,000. And just multiply by 1.15. That will give the overall population, and this number that's 28750. This is my overall population. What is the water use? When we talk about population, it's population equivalent. So it's considered the number of people overall in the community. The gallon per person per day, we need to consider in this case both the residential and commercial. So for that information provided, we have 70 gallons per person per day plus 10 gallons per person per day. That's going to be our water use, water production, right? Now the peak factor is provided to us. So the average itself gives us 2.3 MGD, where MGD stands million gallons per day, which is pretty much 80 by this divided a million, right? Since I wanted the peak, I need to consider the peak factor that is 2.5. So I'm going to have 2.3 MGD by 2.5, which is my peak factor. And so we have 5.75 MGD. So the number in the list, in this case, is D, right?
What is the P times Z?
This here. So this is the gallon per person per day. So it's the water use of an individual. So in our case, it's provided, right? The daily flow rate is not really daily flow rate. It's gallon. It's water use. It's the gallon per person per day used. We will use similar number for water supply. Usually, the wastewater, it's less than the water that we use, potable water, just because some of the water goes for irrigation and stuff like that, but we can use that number. And this is usually is provided like that. If it's not provided, 100 to 120 gallons per person per day usually is the estimate that is used to design. All right? So this is just a flow calculation to size a plant. We use peak flow oftentimes because a lot of our system are hydrologically driven, so we need to know what is the flow overall also at peak. All right. So calculation of the flow, we're good. So let's try to do a second problem. So the second problem, say design overflow rate criteria of 1,500 gallons per day per square feet for peak flow and 1,000 gallons per day per square feet for average flow rate are to be used to design a primary clarifier. So again, just remember the primary clarifier usually circular or rectangular clarifier are tank, circular, sort of cylindrical tank that have this shape or slanted bottom, or rectangular. Again, it's not straight the bottom, it's actually like this. Water comes this way and leave from the weir on top, and here leave usually on the side. Enter from the middle, distribute it, and then the water exits on the top, and the solids are collected at the bottom. So it's just a physical separation to settle heavy, settable solids, right? What is the design based off? The design is based on what we call overflow rate. As the word say and the unit gave us, it's the flow. It's the flow over the surface area. So these are plan view, right? This is my area. If this is rectangular, on the top, this is my area, right? This is my area up there. Surface water, surface flow. This is the area, the circle. So this is front view, plan view, front view, plan view of the clarifier, either circular or rectangular. And overflow rate is the flow that is treated over the surface area. The design of clarifier is based on this. What does it mean, the design? Well, I can size the area, so I can pick the right size clarifier based on the flow that I need to treat, because that depends on the people that I'm going to have to serve. And the overflow rate is given by design guidelines. In this case, is given to us the overflow rate for peak flow. It's the peak flow rate over the area, and the overflow rate average is the average flow over the surface area. So the problem is telling us that we need to design, which means we need to determine the diameter, where in this case a circular clarifier designed to treat the flow. So we wanted to treat a flow of 1 mgd. That's the information that is provided, right? We have a peaking factor of 2.5, right? That's the information that is provided. And the design criteria, so these are set value essentially by the, in New England will be the, can't think about the name, the New England Pollution Control, like they have a manual that will give you the guidelines, so what is the range of overflow rate. You want 1,000 gallons per day per square feet, 1,500 gallons per day per square feet. What does it mean? The overflow rate, every square feet of clarifier can treat 1,000 gallons per day under average condition. Oh, did I invert it? Yes. I was considered this average. This is 1,500, this is 1,000, right? Under peak flow, you can only treat 1,500 gallons per every square feet of area. Under average flow, you can treat 1,000 for every square area, right? So now, how do we determine the diameter? We have two design guidelines. We need to make sure that we pick the size that satisfies both, right? So these are the maximum overflow rate that I have to have. So I need to make sure that I pick a diameter of a clarifier that satisfies both, right? So how do I do that? Well, my area under average and my area under peak condition. And let's see which one is larger. Of the two, I would have to pick the one that is larger, right? Because then will give me an area that will satisfy both, all right? So I just need to, in the case of the average, will be the Q average over overflow rate average, and this is Q peak over overflow range peak. We will do both calculations. You can probably, once you put all of them, you know which one is going to be larger. But so average, we have 1 mgd. And now we need to make sure we have a unit consistent, otherwise we have to do a unit conversion. So we have, oh no, it's gallons, so it's okay. So 1 mgd, we have 1 million gallons per day. And under average flow, it's 1,000. Right? Gallons per day squared. So my area of overall area, it might be multiple clarifier, but that's my area. My peak, we know how to do the peak, is the peak factor multiplied the average, right? So it's 2.5 for a million, so it's 2.5. In this case, we have 1,500 is my overflow rate under peak condition. Again, gallons per day per square feet. That gives me 16.6 square feet. So of the two conditions, the more restrictive would be under peak flow, right? Because I need if I do a 1,000 square feet tank, my overflow rate under peak condition will be higher than 1,000. Higher than 1,500. So I need to make sure that I can size properly, and I have to pick the largest of the two. So this one is more restrictive. So that it's a PD squared over 4. That's my area of the clarifier, right? And it should come to 46 feet. If you did it that part, it will come to be 36 feet. That is one of the options. So you need to make sure that it is this one, all right? Because if I do peak 36, I will see that my overflow rate will be coming more than 1,500. All right? So clarifier design is always based on overflow rate. Both primary and secondary clarifier are based on overflow rate. So this is how we size. And usually the depth is pretty much a standard, like there is a specific, because that efficiency, theoretically, it's independent of the depth of the clarifier, but depend only on the area. So that there is a minimum depth that it's used to avoid turbulence and resuspension and allow the mechanical equipment at the bottom for removal of the sludge. But for the most part, it is just the area that it's sized. Okay, so another problem on clarifier. So we have, what is the average hydraulic detention time for a rectangular tank with dimension 2.5 by 15 by 3, receiving a flow of 900 meter cubes per day? The hydraulic efficiency of the tank is 83%. So we have a rectangular tank. Another parameter that we use, not much for design, but mainly for operation, to get a sense of where it's the hydraulic residence time. The hydraulic residence time, it's the volume of the tank over the flow rate. This is the, we can call it T, okay, is the average time that the water spent in that tank, right? And it in minutes or hours. Just for reference, the Green chamber, 3 to 5 minutes residence time. Sedimentation basin, 1 to 3 hours. That's the time that the average water spent in that tank. But this is if it was a perfect system. So this is the theoretical residence time. In reality, the shape, you could have some water spent there 2 hours, some 1.5 hours. So there is some what we call efficiency of the clarifier, which depends. If we design perfectly, and would be 1 or 100%, but the efficiency usually it's less because you're court circuiting, and depending if it's elongated, it depends on different factor. And usually we do a trace analysis to determine what is the efficiency. So the actual, so this is theoretical, HRT actual is going to be the HRT theoretical multiply the efficiency. Which is a parameter that is usually experimentally determined. Well, calculation. So we have, this is pretty much the definition of HRT, right? Residence time. Volume is given to us as 2.5 by 3 by 15. So 2.5 by 15 by 3, that's my volume. And that's going to be meter cube. And the flow rate is 900 meter cubes per second. Oh, per day, sorry. It's per day, so that's 0.125 days. The answer is given in hour, right? So 24, that's 3 hours is the theoretical residence time, which is one of the options, but it's not the actual residence time. We need to consider the 3 by the efficiency, 0.83, 83%. So that will give us roughly 2.5 hours, which is B, right? So it's the hydraulic residence time. Yep. Yeah, HRT stands for hydraulic residence time. Is the average time that the water spent in that tank. And theoretically, it's volume over Q, but the shape, the way they construct it, it's going to change how much the average time that the water is spent in there. So the efficiency gives us a sense what is the actual time of the water in there. Because you have coarse circuiting and some water. All right, so well, there was a hint, I guess. The average detention time will be less than the theoretical detention time. So if you knew what it was at the theoretical, well, you should be fine. All right, so we're done with the clarification or sedimentation. Same principle, primary or secondary. The next problem 4, 5, and 6 are all related to the biology and some definition, operational definition, and process. All right, so problem 4 there. It's asking us what is the volatile suspended solids concentration of this following wastewater sample. We are given all sort of information, sample volume, filter, sample volume evaporated, mass of dry, a lot of different things. In order to be able to solve this problem, we need to know what are volatile suspended solids and how we measure. So if I have a water sample, a wastewater sample, the wastewater sample will have total solids. The solid present in the water are the total solids. If I filter those solids, and the size, the pore size is a specific standard, usually 1 micron opening. I'm going to have the total dissolved solids and the total suspended solids. The total dissolved solids are the solids that are so small that are going to pass through my filter and be present in the water. The total suspended solids are large enough that can be taken away in the filter so that we can collect it in the filter. The suspended solids, we can also divide them in volatile suspended solids and non-volatile suspended solids, depending if you can burn it or not, if it's organic in nature or inorganic in nature. So volatile suspended solids means that they can be burned, and so usually it's organic in nature. Non-volatile suspended solids, it's inorganic and it can be burned. So the problem was asking us to find the volatile suspended solids and give us a lot of information. So how do we do this procedure? And once you know how volatile suspended solids are determined, it's easy to understand what are the data. So I have my water sample. If I weight the tank, this little container, and I let it evaporate all of the water, and I measure the residual, and I do the difference, I'm going to have the total solids. Not what is asked, right? We want a suspended solid. So I have a certain volume, and that volume goes through a filter apparatus. I mean, it doesn't matter how it is drawn, but a It's a filter set up. So it goes through a filter, right? So this is my small filter that I'm gonna pour the water in, right? This is, I'm gonna call A, the weight of the filter itself. Usually we put the filter in a little crucible to transport. So I'm gonna call A, the weight in gram of my filter, and crucible. I pour now, using a filter column, the water and on the filter. Now all the solids that are suspended, or the tiny one that dissolve, are gonna pass through. But the solids that are suspended are gonna stick on the filter, right? So these are just filter. I'm gonna put this at 105 degrees Celsius. What does the 105 degrees Celsius do? Put it in the oven, you remove all of the water. What I'm left, I can measure my B, the weight of the filter, right? Plus crucible, plus total suspended solids in terms of gram, because I can weight that, right? Here I had only filter plus crucible. Now 105 degree only allowed to remove water. If I now place this at 550, what happens is that organic will burn and only the non-volatile will stay. So I'm gonna have a little left, and if I call this C, I'm gonna have the filter plus the crucible plus the non-volatile suspended solids, whatever is not burned. Now if you read now my A, B, and C, what I do correspond to. Now that volatile suspended solids, I can find as, because TSS, right? TSS, it's VSS plus non-VSS. So filter and crucible weight, TSS minus NVSS is gonna give me the VSS in gram, right? So if I put B minus C, right, the gram, what I weight here and what I weight after 550 is the non-volatile, it's the volatile suspended solids in terms of gram. VSS, it's a concentration. We need to consider how much we filter at the beginning. So that will be the gram or milligram per liter of wastewater. Now, in this I use A, B, and C just to, what is in all of it, it's written there. So the VSS, if you look, MSS is the mass of dry crucible, filter paper, and solids. MSI is the mass of ignited means burn at 550, crucible, filter paper, and solids. So it's exactly my C. And then the volume filter is VF. All right. So now we can look at the number. So MSS was 25.645 gram minus MSI 25.501 gram divided 0.200 milliliter, which is 0.2 liter. So it should be 720 milligram per liter. I can just take that, and that becomes milligram, right? Just multiply by 1,000 and I have milligram. All right? If there were multiple questions from here, from all this information, you can also find that suspended solids, you can find the total solids, you can find the non-volatile. So it could have been multiple.
What is TDS?
What?
What is TDS stand?
Total dissolved solids. It's mainly like calcium and magnesium present in water. It's more important. TDS is more important in water treatment than it is in wastewater, but we don't usually measure TDS in the residual. It's mainly for potable water, drinking water. So in that case, you will burn the whole thing and measure this with or without the sample. And that the difference will give you the actual solids. All right? Now, volatile suspended solids. If we talked before, we talked about total suspended. Why do I care about volatile suspended solids? Well, volatile suspended solids is a measurement of the organic solids, and usually bacteria or bugs are expressed in terms of volatile suspended solids. So the volatile suspended solids give us a sense of the bacteria, the biomass that does the process in the biological process. So VSS, it's a unit that we will need in the next problem. Alright, so I'm going to redraw your secondary process. What I draw on the board and what you have in the handout, it's what we call secondary process, or the typical secondary process that we use is the activated sludge system. Activated sludge system is both a combination of the biological unit, the aeration tank, and the secondary clarifier. How does it work, the process? I have my flow with my BOD concentration, my suspended solid concentration, in the aeration tank I add air. organic matter present in the wastewater, we represent we measure the strength of the organic matter in BOD, biochemical oxygen demand, which means pretty much the oxygen that will be needed to oxidize completely this organic matter, right? We might have sugar, protein, fat, all of those are organic. Instead of measuring how much sugar there are, how much protein there are, we measure the oxygen that will be needed to oxidize that organic matter. So biochemical oxygen demand, okay? So the organic matter can be expressed in milligram of oxygen per liter. That's oxygen in air. So air provided. Right? Organic matter, organic substance will have at least carbon, nitrogen, oxygen. It could be also nitrogen, be like more complex, but the organic matter plus oxygen can be oxidized to CO2 and water. If this is a biological reaction, who is doing this this transformation are bugs, bacteria, do that process. The bugs are already present in wastewater, and they can grow pretty fast, right?
What is chlorine?
What?
What is that? Is it C2H?
This? I just wrote CHO, CXHYO, like a generic organic compound, right? If I do a stoichiometry, if I add exactly the composition, what I can do a stoichiometry of this reaction. Usually we don't measure the composition, we just measure BOD. All right. CO2 plus water. We are aerobic, right? That consume organic, right? We breathe, we use oxygen, we release CO2 and water. Now, energy, it's released so they can be used by us to move and also by the bugs. Now, we don't produce as fast as bugs do, thank God, but bugs produce pretty quickly, right? So, the organic matter, BOD, is going to be transformed, adding air into CO2 and water. CO2 will be released, right? Water, no problem. Bugs. Bugs, it's organic matter. The difference is that this is soluble, and so it's impossible to remove from the water. This is still organic, as the same X1, Y1, Z1 as NP, like it's a more complex organic. The different, now this is in particular form. It's a solid. How do we remove solids? Physically remove it in a clarifier. So the secondary treatment allowed essentially to transform organic matter from soluble organic matter to CO2 and water. So some of the carbon goes here, some of the carbon goes to build new bacteria. Now, bacteria we have limit on solids, right? So we need to get rid of them. The clarifier remove the solids. So if X is the TSS, let's say we have 200, we have here 100 after that 50% removal in the primary clarifier. Within the reactor, we have a lot of bugs that are eating the bacteria. eating the BOD. So my X, because X stands for suspended solids, it's very high. My S, BOD, it's pretty much 95% removed, so 200. Let's say we have 20. That's 2,000. X goes XE, 20, SE, 20. X down, a lot higher. Right, usually 10,000, 7,000, oh, I don't, yeah, 7,000 to 10,000. So what we are trying to do is transforming these BODs, this organic, that if released into the environment will consume oxygen, producing anaerobic condition in the river, will transform from soluble, using bugs, into new bugs that are solid. And then we send everything to a clarifier that will settle out the solids that can be removed. Now, this line here in the anaerobic, this is the most complex of this part, especially if you haven't done activated sludge in a long time. This line here, water and bugs are returned at the beginning of the plant to increase the capacity of treatment. Because either I do this very big, or I need to concentrate a lot of bugs in there to make the process faster. So a way to do that is what we call the recirculated activated sludge line, and we send back bugs at the beginning of the tank. We don't want to accumulate too much, because if the concentration grows too high, you will not be able to physically separate it. So you can have a very fast removal here, but if I cannot physically separate it at the end, it doesn't make much sense. So there is a physical limitation to how much bugs we can incorporate in there. So 2,000 to 3,000, it's typical, the concentration of volatile suspended solid of bugs that I can keep in there before your clarifier crashes, essentially. And then you will have solids out. All right? So this is what an activated sludge system looks like. To maintain a constant concentration, some bugs need to be wasted. At the bottom, we have what we call wasted activated sludge. Which is also secondary sludge. All right, so this is the process, and those are all the characteristics.
Are these bugs organic or synthetic?
It's organic. So the bugs are already present in wastewater. There are millions of bugs already in wastewater. So you don't need to add any bugs. At the beginning of the plant, when you design the plant, it will take some time to get the right concentration. So there will be a transient time to build up the population so you don't waste anything. But after a couple of weeks of operation, you would achieve enough bugs there that can sustain the process. So it's just all different types of microorganisms in there that will feed, that will eat that BOD. All right? So it's the same process that happened in the river. The difference is that we add air. So we speed up the process providing enough air, and we speed up the process because we are concentrating bugs in there. Instead of having million, we have trillion of bugs in there. All right, to do the process. Now, all of this was the theory of this. Let's try to do a problem. Let's see if we understand some of the problem. So So we have a 10 mgd activated sludge plant. An activated sludge plant looks like this. Has an aeration tank and a secondary clarifier. The following operational design are chosen. The mixed liquor, volatile suspended solids. Mixed liquor is the mixed liquor is the liquor, the sludge, the bugs, and the wastewater in this tank. That's what is the mixed liquor. VSS is volatile suspended solids. So mixed liquor VSS is pretty much the bugs in the aeration tanks. $2,200 milligram per liter. So, all right, let's use these two so we can correct that. Right? The influent BOD concentration is 200. Now, that's not correct in our case. What we are talking is Q influent before raw wastewater coming in at the plant. The flow rate to what it was, 10 mgd. 10 mgd plant, S influent is 200 milligram per liter, of which 35% is removing primary clarification. You remember when we did the primary? We say that some of the grease and oil it's removed on top, that's organic, that's BOD. Some of the organic might settle out with other solids, that's organic. So 35% BOD is removed in the primary. It's not designed to remove BOD, but we have BOD removal. The food to microorganism ratio in the aeration basin is 0.2 per day. We wanted to find the volume. Food over microorganism ratio, it's a design parameter, actually more of an operational, but can be used for design. Food over microorganism. What is the food? Is the BOD that comes in to the bugs to eat is the food. If I call S naught the concentration of BOD coming in to the aeration tank, that's the concentration of food. The mass of food will be the Q S naught. That's the kilogram of BOD coming in. The kilogram of organic matter coming in. That's my food for the bugs. The microorganism is the mass of solid present in the aeration tank. If X is the concentration of mixed liquid suspended solid in the aeration tank, the microorganisms that are eating are going to be X, the concentration, multiplied the volume of the aeration tank. I do not agree with the day theoretically because it's kilogram over, this is kilogram of BOD and this is kilogram of VSS. I mean, it's kilogram over kilogram and there is a way to convert one to another, but It's okay. Sometimes it's written as a per day. I do not agree with the unit that are given. It's not really perfect, but we're gonna make it work. All right. So per day, this is provided. It's a design parameter. Volume is what we're trying to determine. The problem for this, and for most of wastewater activated sludge, it's understanding what is given to us, essentially. It's like two equations, but there are all this symbol. You need to understand what it, and that's why I spend some time on explaining the process. So the volume of the aeration tank is going to be QS naught F over M by X. Especially because a lot of these problems have not just these data that provide a lot of additional information, because maybe there are 3 or 4 questions all related to this problem. And so in this problem, everything that is provided is useful, but oftentimes you would have a problem that has this and other 4 other data and that are needed not for the first problem, maybe for the second and the third. So understanding what everything means, it's important. All right, so do we have the flow rate? The flow rate is given, it's 10 million gallon. Do we have the concentration of BOD coming in the aeration tank? 200 is the influent. So it's going to be 200. It's 65% of 200, right? Because 35% is removed. So if it's removing the primary clarifier, it's not going to be food for the bugs, right? So it's just the S naught. So I'm going to have 1 10 to the power 6. That's my gallon per day. Gallon per day. S naught is going to be 200.65, right? Milligram per liter. This is 0.2, 1 over day. And X, it's our mixed liquor, volatile suspended solids. That's what is given to us. That is 2,200 milligram per liter. Now you can see that I'm removing this milligram with this milligram, and they are not the same thing because one is milligram of oxygen, 1 milligram of solids. It's because this unit is not, I don't agree with that unit. The only way that I could remove all of this, if this unit also had milligram and milligram, we should have. It is milligram, but it's not milligram of the same thing, right? But we'll accept that. And day goes, I will have tank. This is 295, right? 454 gallon. Of course, the problem is given in cubic feet. We need to 295 divided 7.48, right? That conversion between cubic feet and gallon. Multiply, because 1 cubic feet, it's 7.48 gallons. So we would have a 395, is that right? So, okay, did I mess it up?
Use a million, not 10 million.
Oh, that's why. Okay. Okay, so that should come back. It should come out right? So it's 395,000 cubic feet. Beside, we're not doing a problem, but just because it's either this problem with the F over M or the definition of SRT, large H, that it's usually this problem. Sometimes instead of design based on F over M ratio, we design based on sludge H or solid residence time. HRT is the average time that the water spend in the system. SRT, sludge H, is the average time the bugs spend in the system. V is the volume of the aeration tank. X makes liquor. SRT, it's our design parameter. Over here is the sludge that it's wasted. So this is the so some problem will just give you secondary sludge. It's 300 kilograms per day. So pretty much you are given this. So if this previous problem was giving you also that secondary sludge, you could have determined the volume based on SRT. So it's another design. Or it could have give you the flow rate of the Q. And XR is the mixed liquor concentration of the recycle line. So it depends on what the problem give you. You can use different equation. I don't have a problem with this, but just to mention, because oftentimes it's either F over M ratio or SRT problem. But it's identifying what it's provided to you, essentially, in this problem. All right? Any question about active sludge? There's not going to be anything like this on the morning, so if you're worried about, I doubt it that there will be. If there is anything in the morning, it's like HRT, like very simple. Anything related to bioprocess, it's usually for the environmental afternoon session. Not much on that morning, more simple calculation type. All right? How many years ago you did the last chemical reaction? Well, we're doing one here. We're almost there. Only 30 minutes. I did 6 hours of lecture today, so this is my last. So I'm ready to go too. All right, so problem number 6. This is more advanced. Again, this is again more afternoon kind of problem. Say the full nitrified influent to anoxic basin contain 25 milligram of nitrogen. The following equation apply. So nitrogen, it's one of pollutant present in wastewater. And nitrogen we say mainly as ammonia, and organic, it's present in wastewater. Nitrogen can be removed in an aeration tank, similar to the one that we have just saw for BOD removal. Ammonia plus oxygen plus bugs. He gave us nitrate plus water plus bugs. This process, it's called nitrification. It's the biological oxidation of ammonia into nitrate and nitrite. It's two-step process, so it's more complex than just one step. So when it says fully nitrified influent, means that I had it 30 milligram of ammonia coming in. The ammonia has been oxidized into nitrate. I have 25 because 5 went to build up bugs, right? Some of the nitrogen, it's part of the bugs itself. This is not removal of nitrogen, it's just conversion. We go from ammonia to nitrate. Some plants will just require you to nitrify your wastewater because its ammonia is toxic to fish. Nitrate is not. So if you are concerned with toxicity, you wanted to do nitrification. So you have ammonia converted into nitrate. Now if you are concerned with the nitrogen creating algae and algae bloom, so nitrogen present as a nutrients that can produce nuisance, algae bloom, and problem in the receiving, the nitrification won't solve that because you're going from ammonia to nitrate, and nitrate is still available to plant and algae to pick up. So nitrification is not going to be sufficient. So what do? It's add an anoxic tank, so no air, because nitrate plus organic produce bugs produce nitrogen gas. Nitrogen gas is going to be released in the air, so you won't have nitrogen in your receiving stream. The organic needs to be added because we have just added a bunch of air that has oxidized all of the organic that we originally had. So in this schematic, the way the problem, what do you see the organic in that equation? That's methanol. Methanol, it's a chemical that it's added to provide organic to oxidize, to reduce nitrate into nitrogen gas. Okay, so and there are different schematic of this nitrification, denitrification, because if I put this before, I can use the organic, but I have to recycle because I don't have the nitrate. So there are all different type of process to do removal of nitrogen, but one simple one, it's I nitrify and then I denitrify. I add air, convert, I add methanol and convert nitrate into nitrogen gas. So this is the concept of nitrogen removal. So nitrification, denitrification. The problem is pretty much a stoichiometric equation. So it tells me, it's asking us to find the minimum methanol requirements, how much methanol I have to add to provide complete denitrification. So this is ammonia to nitrate. That's nitrification. Nitrate to nitrogen gas. denitrification. There are two biological processes done by different type of bacteria. The first one, aerobic bacteria. They need oxygen and ammonia. The second one, it's denitrifying bacteria. They need nitrate and organic for the process to occur. Now let's see, with all the chemistry in you, I hate chemistry too, and I'm an environmental engineer. I'm a bio person, so. But let's look at this equation. If you look at the stoichiometry of the reaction, what is telling me, if you remember a little bit of chemistry? It's telling me that I need 1.08 mole of methanol, right? If I read that equation, I have 1.08 mole of methanol for each mole of nitrate, right? That's what that stoichiometry reaction is telling me, right? I need 1 mole of methanol for each mole of nitrate that I need to reduce to nitrogen gas. But the problem is asking me to find the milligram. How do I go from mole to gram? Well, we need to use molecular weight, right? The molecular weight gives us that gram per mole. So we need to use the molecular weight. Molecular weight, so we have 12 plus 3 plus 16 plus 1, that's 32. That's the gram of methanol for every mole of methanol, right? So if I multiply by 32, then I have the gram every mole. Oh, I should have just, I'm very not straight. So now I know that I need 32 gram of methanol for every mole of nitrate, right? But what we started is we have 25 milligram of nitrogen, right? So if I have 25 milligram of nitrogen per liter, right? I don't have 1 mole of nitrate, I have 25 milligram. So I need to use again the molecular weight, in this case of nitrogen, right? To go from the finding how many moles is 25 milligram, right? Nitrogen is 14. We have the gram of nitrogen, or mole of nitrogen. Now the fact that it's NO3 and N, I use 14, that it's the mole of nitrate, of N. But I have only 1 mole of N for each mole of nitrate. So I should adding 1 mole of N per 1 mole of NO3, just to be consistent in terms of unit. Because there is only 1 N in NO3. So there is 1 mole of N, oh, sorry, 1 mole of N, 1 mole of NO3. So that I can cancel out that mole of NO3. Mole of NO3, mole of NO3, mole of N, mole of N. I have gram and gram, so those gram go away. So I can find, I don't have to do any change it in unit, because my gram and gram go, milligram stays, milligram per liter. I can write down 1 millimole per 1 milligram. So a little bit of chemistry, but if there is problem, it's going to be the what is nitrification and what is denitrification. All right. All right. We have last two problems. Stay with me. All the water line produce residual. The residual at a wastewater treatment plant are mainly bio waste. Well, it's sludge that it's biologically active. Primary sludge and secondary sludge. We cannot dispose as it is. Mainly, it's just water, essentially. So it's not very convenient to track out all this gallon and gallon of water. But also, it cannot be disposed without further treatment. So sludge treatment needs to be stabilized, remove the pathogen in primary and secondary sludge, take all the water out so that you can have a solid that can be moved in a truck and disposed either at a landfill or at an incinerator. The almost last problem is talking about the primary sludge. Whatever it's removed at the bottom of the clarifier needs to be further treated. One way to treat it, it's usually sent to a decanter, like thickener, to remove excess water. And then after you remove excess water, the bottom sludge is going to go to an anaerobic digestion. The giant eggs at the island, those are anaerobic digestion. It's a biological process where bugs eat bugs, essentially. You have your sludge that it's organic. You put it under starvation condition, under anaerobic condition, you will have bugs that eat bugs. At the end, you'll have a minimum amount of bugs and CO2 and water. So those are the process of anaerobic digestion. Here is the design of anaerobic digestion. Primary sludge is treated by anaerobic digestion. So I have solids, and it's transformed in biogas and solids. If you start with 1,000, you end up with 100. So now you have to dispose a lot less, right? So that's reduced significantly the amount of solids that we have, and produced biogas can be used for energy. All right, that's anaerobic digestion. What information is provided to us? The following data applied. Theta C is the sludge age or residence time of the sludge in the anaerobic digestion. Typical anaerobic digestion is done in and out without recirculation. So the residence time, it's like the hydraulic residence time, V over Q. So a lot simpler than the other bioprocess that we saw. So theta C, 14 days. Volume of digester, Q of primary sludge. The flow rate of primary sludge, in this case treated, because we're treating only primary sludge. The moisture content of primary sludge, 95%. What does it mean, 95%? We only have 5% of solids. Essentially, we have 5 grams of solids every 100 grams of sludge. That's 95% moisture content. So 5% solid content, right? That's what it means. Moisture content, so is the water percent, so 5% solids. All right. The specific gravity of the sludge is 1.05. Very similar to the specific gravity of water, right? The dry solid remove here are 6,500 pounds per day. So the solids, not the water and the solids, just the solids are 6,500 pounds per day, dry solids. All right? What is the volume of the anaerobic digestion? To find the volume, I have the residence time, 14 days. I need to find the flow rate of primary sludge. Flow rate in cubic feet per second per day. I know how many pounds of solids are in the primary sludge, but I need to know how many cubic feet of primary sludge, that it's water and solids, coming in, because that's my flow rate. What comes in here is not just the dry solids, it's the solids and the water. So it's just a unit conversion to go from the pound of solids to the cubic feet of sludge. So cubic feet of primary sludge, how do we get that? So we start with 65 pounds of solids, right, per day. Only 5% of the sludge, it's solids, right? So I have 5%, I can say that it's 5 pounds of solids, right? 100 pounds of sludge, right? That's the water content. Now it gives me from pound of solids to pound of sludge, right? The water and the solids, right? Pound, pound. I have now pound per day of sludge. How do I go to the feet? I need to do the specific weight, right? It's gonna be, okay, we need to find that. It's 105, 5. We need to consider the specific weight of water, that is 62.4. That's the cubic feet. Sorry, it's the pound per cubic feet. Pound of sludge per cubic feet of sludge. So pound and pound go. I have cubic feet per day. This was just the unit. At the end, it's just looking at what you're given and what are the units. So at the end, it comes to be 1984 cubic feet per day multiplied by 14. By 1984 give you about 27,800 cubic feet. Is that clear how we did it? It's just a matter of conversion because you have the dry solids. You wanted that wet sludge, but you don't want it as a weight. You want it as a volume because that's the flow rate. The volumetric flow rate is needed to determine the size of the tank. Anaerobic digestion. It's always like, it's a simple calculation because it's just based on HRT. And so it's, at the end, it's always this type of calculation. Knowing what its moisture content means, knowing what specific gravity is, right? All concept that as awfully as civil engineers we have, more or less, right? Better than chemistry, right? We have the last 6 minutes, and I use them all so that you pay for this 2 hours, so I'll give you the 2 hours. I'm dying here, but we'll do it till the end. All right. Oh, we have treated all of this, and now we're discharging into a receiving stream. The last problem, we have an industry is proposing to discharge its effluent into a nearby stream. So we have this wastewater, and they wanted to discharge into the receiving stream. The flow rate, so I have a stream here, and I have an industrial wastewater that wanted to discharge into this stream. Q, industry, it's 10 mgd, and the BOD of the industry, it's 100 milligram per liter. The stream itself has a flow rate of 100 CFS and a concentration of BOD 2 milligram per liter. It's saying that in-stream BOD standard has to be less 5 milligram per liter. So maximum concentration of BOD in the stream, it's 5. How much the industry need to treat the removal efficiency for BOD to be able to to discharge this wastewater. So this is a mass balance, simple mass balance. We have two flow coming in. So I have this mass of BOD coming from the waste, and I have this from the stream. Down here, I'm going to have my flow that is going to be the sum of the two industry and stream, right? Mass balance, simple on water. The concentration has to be less, right? Less than 5 milligrams per liter. It's asking how much do I have to treat that BOD so that I can discard, can I dispose 10 mgd? It's obvious that if I put 100 milligrams per liter, we're not gonna go, it's not gonna be good. So let's see what is the concentration that I need to discharge to have 5 as an overall. How does it work? It's a simple mass balance. Input equal output. What I have in terms of BOD coming in at this point, I have QS, CS, the kilogram of BOD coming with the stream, plus kilogram industry, right? So this is the mass of BOD coming with the stream, plus the mass of BOD coming with the wastewater. Flow rate per concentration, it's mass rate. It's gonna be equal to the mass rate out of this point, right? After they mix, I'm gonna have given concentration and the flow rate. This is fixed, has to be less than 5. This is fixed, the river it's what it is. This is fixed. This is also fixed because that's the industry flow rate. The only thing that we can change is that concentration of BOD coming in and can be done through treatment, right? So CI is going to be QS, CS minus Q. Oh, I am using stream and stream. Oh, shoot. I'm going to use downstream. Sorry. Didn't realize that I was using the same symbol. Minus, okay. Let's see. That now it's QD, CD minus QS, CS minus Q. So I have 10 mgd meets 15.4 CFS. This is just the conversion from gallon to cubic feet. And from per second and day. So I'm gonna have, right? This is QD was why do I have 100 by 2, right? This is 100 by 2, and this was 115, the sum of those two flow rate. QD by CD, it's 5, what we wanted to achieve. And divide it 15.4. That's to get a mixture, so to mix these two flow and the overall mixture have a concentration of 5, less than 5, the maximum concentration of BOD coming from the industry is 24. If I have 100, what is going to be the removal efficiency? 95, 76, 67, or 54%? 76%. So that's what the removal of efficiency that the plant has to do so that the overall, the river is not going to be affected. Usually for discharge in river, it's either BOD limitation or a dissolved oxygen limitation. And it's usually, so it's the same equation, it's just that you have dissolved oxygen instead of BOD. So those are the important parameters. You don't want to add organic loading, and you don't want to reduce the dissolved oxygen of the stream. If you add organic loading, you will decrease the oxygen, and if you adding an anaerobic, like very low DO flow rate, you're going to overall lower the dissolved oxygen. It will affect all the population of fish and stuff like that. So that's one main consideration for water quality. All right. I think we are done. We cover all of the problems. If you have from now until you are doing the exam any problem or question, please feel free to reach out. You have my email. Did everybody sign up? The other booklet that I give you already have the solution. Some of the problem we did, some we didn't, so you have additional. You got it? Thank you. Everybody else sign? No problem. Good luck. Oh, well, I'll see you guys actually in a couple of weeks.
Quick question for you. That
Yes.
email you sent us before class, did that have some more practice problems? on
Yeah,
it?
there are some additional practice problems. There is, I think, one or two that are
Okay.
the same, but some additional problem with the solution already. And the package has like some handout, but I mean, if you have this, so that's okay.
Sure.
Yeah. No problem. Yes. Oh, here it is. Do you remember anything, Emily?
I talked to you those stuff. 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 I talked to you those stuff.